Okay, so is that...
Yeah, please.
Okay, thank you. Well, firstly, thank you for inviting me to give this talk, and I'm sorry I couldn't be there. I would have loved to come to visit India, and hopefully soon I will be able to. So I thought I would give you an introduction to, I've called it laser plasmas for acceleration and applications, because I think it's important to have a two-pronged attack to try and understand both new science and to develop useful sources from these laser plasma interactions. Okay, so first of all, the science that I do is very international. It's also multi-institutional, and so this can't be done by me alone. And in particular, some of the data I'm going to show today was generated by my PhD student, Chris Baird, and some experimental data analysis was done by Jason Cole at Imperial College from Stuart Mangle's group. So I should definitely recognise their contribution to this work. I'll talk a lot about my own research interests at the University of York. And the three sort of main prongs of research that I conduct and with my group at York are laser plasma interactions at the intensity frontier. So I'll talk a little bit about what happens when intensity increases. I guess you should have learned quite a lot about this from Anton Elderton and maybe from Bob Bingham as well. But I'll go over a little bit of the basics as I understand them. I'll then talk about how that can be extended to electron, photon, and radioisotope sources, and whether or not in this quest for greater scientific knowledge, we can also produce some interesting sources that could be useful for industrial and maybe even medical applications. And finally, the third part of my research is about laser plasma nuclear physics. I won't have very much time to talk about this, but I'm more than happy to start an email conversation or have a further conversation in the future about the work that I do with laser plasma nuclear physics. So studying how plasma effects can cause changes in nuclear half-lives and nuclear reaction rates. But the other reason that I find it useful to collaborate with my nuclear colleagues at York is that I feel that in order to advance laser plasma acceleration, we're going to have to understand the sources we generate better, which is going to be an improvement in diagnostics. And the best people I know at diagnostics tend to be nuclear physicists. So I'll talk a little bit about how they might help us and how we could provide testbed facilities for novel nuclear diagnostics. So I'll start by talking a little bit about laser plasma interactions at the intensity frontier. And from my perspective, the interesting parameter is this quantum parameter chi. And I define it here as being the strength of the field, be it electric or magnetic or laser field in this case, relative to some critical field, often known as the Schwinger limit. And we know that when chi approaches 1, or when the laser field approaches the Schwinger field, interesting things start to happen. Quantum effects start kicking in, radiation reaction becomes important, and pair production becomes prolific. And so this would be interesting. The problem is that this intensity equates to a laser intensity of something like 10 to the 29 watts per square centimeter, which is, even by the most optimistic viewpoint, is several decades away if it will ever happen. But we don't just need to rely on the laser intensity to provide these strong fields. We can also provide a strong field in the frame of a moving electron. And in this case, the electron witnesses a field that is gamma times larger than the field that we witness in the lab frame. And this is interesting on a very basic level because anytime you have a strong laser field interacting with the plasma, you automatically have electrons that are accelerated. And so this gamma factor can become quite large. For a normal laser plasma interaction, we can say that the gamma factor is approximately, broadly speaking, the A naught of the laser. So it's the oscillation velocity of an electron inside the laser field. And so we can reformulate these equations, and we can say that the chi factor is proportional to A naught times intensity to the half power. And if we put in all the numbers, we can show that the chi becomes important when the laser intensity reaches 10 to the power 23 watts per square centimetre, which could be interesting for next generation laser facilities such as Apollon and DLINP and several others that people have been proposing in many countries around the world. So why do I think studying this chi parameter is interesting at all? Well, there was a paper written by my colleague at York, Chris Bridgers, and he suggested that from simulations, as the intensity of the laser reaches 10 to the 23 or 10 to the 24 watts per square centimetre, the oscillation of the electrons in the laser field becomes so extreme that they start radiating a large fraction of their energy as gamma rays. So at 10 to the 23, you can convert about 10% of the laser energy straight into gamma rays, rather than going through any intermediate, ions or fast electrons in particular. And at 10 to the 24, that fraction goes up to something like 35% laser energy. Now, while this may open the door to things like positron production and gamma ray sources, if we're trying to follow some of these trend lines and try and increase the A naught in order to get to higher ion energies for ion acceleration, we have to be careful, because we can't extrapolate these graphs to higher and higher A naughts, because the energy will no longer couple as it currently does into electrons and then into ions. Instead, it will convert straight into gamma rays, which do not interact with the target. And so while ion acceleration could scale with energy, it certainly won't continue to scale with intensity in the same way as it has previously when we reach intensities where this chi parameter becomes important. So I think there's a very good case to say this chi parameter should be interesting, but there's also a good case to say that we can't study it in a laser solid target interaction at present. So as an experimentalist, what am I doing? How can I try to understand this process when I can't reach the intensities of relevance? And the response to that is, well, let's look at this equation again. And let's not assume that the gamma is provided purely by the electric field and the magnetic field of the laser. Let's assume that we can impose an external accelerating field to the electrons, which allow the gamma achieved by those electrons to be provided by some source other than the A naught of the laser. So if we separate this chi equation at the top into two separate terms, where the first one is just a gamma, it's provided by a fast electron bunch, and the second term is proportional to the intensity of the laser to the half power, we can see that instead of needing 10 to the 23 watts per square centimetre, we can reach interesting chi parameters with only 10 to the 21 watts per square centimetre, as long as the electrons that interacts with have energies approaching or exceeding half a GeV, so 500 MeV. And so this is where one big branch of my research is headed. So what we need an electron beam that's fast, and we need a laser that's intense. And so the obvious option is wake field acceleration. This means that we can provide highly relativistic electrons and provide them in a target area where an intense laser is available. And so that's what we do. And a quick overview of wake field acceleration, although I understand there have been several talks on wake field acceleration already, but I'll take it back to 2004, to the glory days of the Nature paper and the Dream Beam. And the point of this is to make it clear that you want to drive a wake field, you want to provide electrons into that wake field, probably by self-injection. And if you can grow the wake field slowly and inject carefully, then all the electrons see the same potential, and you end up with a monoenergetic electron beam at the end of your wake field accelerator. And it's important to do this slowly if you want the quality of the electron beam to be high. If you drive these wake fields with too high intensity or too quickly or too high plasma density, you end up with multiple positions of wave breaking in multiple buckets, and you end up with either a spiky spectrum or indeed a thermal spectrum. So to show how this works in our simulations, I've got a simulation using the pick code EPOCH. This was run by my PhD student, Chris Baird. And you should be able to see the laser going from left to right. At this point, the box starts moving along with the laser. And in this case, it's the electrons in the second bucket that inject. And we can accelerate these. And I think this gets to something like 100 MeV or 200 MeV in the space of around a millimeter or two. And so we've shown that we can demonstrate electron beams. We've done this both in simulation and experimentally. And so we can collide them with a laser pulse. And that's what we did. So last year, we took this experiment in conjunction with Imperial College to the Gemini laser facility. This top image shows a cartoon of the experiment from left to right. I'll describe it. We've got a long focal length. This is f40 focused onto a gas jet to provide laser wake field acceleration. This provides electron beams between 400 and 700 MeV. The electrons then leave the gas jet and continue on into the vacuum chamber, at which point we have a collision. So we have the second Gemini beam that's focused in the opposite direction, focused down onto the electron beam. You'll notice this second parabola has a hole in the middle. This was not accidental. This was deliberate. We got a hole drilled in the parabola so that both the electrons could escape through the center of the parabola into the diagnostic suite, and also so that the F40 beam, when it expands, goes through the hole in the parabola and is not reflected back into the laser chain. It's important both for the laser safety and for the design of the experiment. The third part of the experiment, when the electrons have been interacted or not with the short focal length F2 laser, they then enter a magnet and are analysed in an electron spectrometer. Any gamma rays or X-rays generated from the laser electron collision through inverse Compton scattering are then detected by a cesium iodide array outside of the target chamber. The bottom image shows a sort of enhanced image of what the focal spot looks like. On Gemini, it's a few microns in diameter and reaches intensities above 10 to the 21 watts per square centimeter, which is peak A naught, in this case of 26. So this is about 8.5 joules in 45 femtoseconds. And so we now have, I'll show you some experimental results. Well, first of all, I'll explain this cesium iodide detector on the left-hand side of the top, in the right-hand side of the top image. It's basically an array of individual crystals. There's something like 30 tall and 40 wide. And if we have a gamma ray or some kind of photon source impinging, as the yellow arrow shows there from the left, then the cesium iodide crystals scintillate. And if we view this from the side, we can tell something about the energy of the gamma rays by how far they penetrate into the cesium iodide stack. And this is just imaged using a sort of standard CCD, an EM-CCD, but we actually didn't have to turn on the gain in order to see this for this experiment. So I'll rotate this round into this orientation when I show you the results in the next two slides. So we measure the electron spectrum and we measure some indication of what the gammas look like using the cesium iodide stack. And here's some experimental data that I've just directly stolen from a slide from Jason Cole, which is why the design of the slides changed a little. The bottom half shows the electron spectrometer signal. So this is raw data, but analyzed against the expected energy from bottom to top. So the low energy, so the electrons which have been deflected the most appear at the bottom of this image, and the ones that deflect the least appear at the top. You'll notice there's a lot of structure on these electron beams. This was not deliberate in this case. It's interesting because if you've got a lot of structure on the electron beams, it probably means you also have a lot of betatron radiation, which could be interesting for applications. It wasn't what we were going for. And you see there's also two broad populations of electrons, sort of a high charge group that's bright white about halfway up the image, and then a sort of a lower charge section which extends up to really high energies, up to 1.5 GeV in some cases. The reason these electron beams don't look particularly nice is we reckon we had a gas jet nozzle which had a small knock in it, a small notch away, and this was causing uneven gas flow and causing density jumps, which caused secondary injection that we did not want. And so that's why the electron beams look a bit funny. The point is, in the top image, there's almost no signal at all on the cesium iodide detector. And these are shots where the second colliding beam, an F2 geometry, was not switched on. If we switch on the second beam, we get these results here, and we see that for more than half the shots, it's clear that the signal on the cesium iodide is significantly increased. There's also a hint here, if you look at the middle 3 electron spectra, that the bright high charge section of these spectra appears at lower energy. So there is an indication that maybe we saw some kind of radiation reaction effects. But I don't want to jump the publication, which is currently in preparation, and I encourage you all to read when it comes out, hopefully in the next few months. But we can do a statistical analysis on all the shots that we took, either whether the collision beam was switched on or off. And we notice here that the red dots represent all the times when the collision beam was not on. And you can see there is some background noise. It fluctuates a little bit between minus 0.5 and 0.5 in this scale. And that means that all these blue dots that extend all the way up to 2, 3, 1.5, 2, and 3 with the collision beam on actually represents a real signal. And as I say, this is a preparation. But to be honest, to do this kind of experiment, to do these really high chi values, you're probably looking at using a dual beam system like Gemini. The interesting side effect, the interesting question is, why did we use the gamma signal in order to determine the collision rather than using the electron signal? And I think from the previous slide, the answer is fairly clear in that the electron beam wasn't very nice. Even with a non-ideal electron beam, it's still possible to see these effects. What you would need, though, is you would need to be able to measure the spectrum of the electrons before and after they collide with a high-intensity beam. And this is where the problem comes. If you've got shot-shot variation, you want to do both before and after collision at the same time. Now, we think we've found a way of doing this, and again, more work by a PhD student, Chris Baird, which hopefully we'll publish soon, has looked into whether or not we can see a difference between the spectrum before and after, but using a single shot. So admittedly, this is an idealized beam, but for this simulation, it wouldn't have to be an idealized beam. The image to the left shows what a GeV beam would look like on an electron spectrometer. This is simulation data. But it shows, using EPOCH, shows what the electron spectrum would look like if it was a GeV with a few hundred MeV, about 100 MeV full width half max. And if we collide it, this electron beam with the laser, but we allow the electron beam to drift a little bit, so there's a correlation between position and angular directionality, I guess, of the electron beam. Then after the collision, we see the image on the right. And the point of this work is to study at what point should you hit the laser with the electron beam with the laser in order to see any radiation reaction effects. In fact, and the point here is if you take the blue line out and the red line out, the blue line out can indicate what the spectrum of the electrons was before the interaction, and the red line out tells you what effect this collision beam has had on the electron spectrum. Now, the problem with all this stuff is that this is an idealized beam, that even although it's not a perfect beam, it's still a lot nicer than the beams that we actually see on Gemini. So this opens the door to some really interesting new physics that we could study, or new optimization experiments that we could complete. In that we need to study the size and reproducibility of these electron beams. We have to work out whether or not we should be controlling the injection, either with a second laser pulse or with density gradients, in order to in order to stabilize the electron beam. And if we can stabilize the electron beam, then we can go and try these experiments again. And if we can measure the amount of energy lost by these electrons, we can actually start putting some numbers in to the radiation reaction effects. And it's by putting these numbers into radiation reaction effects that we can help firm up our understanding of strong field QED. In actual fact, the thing that I think is most interesting about this is that when you collide the electron beam and the laser, you produce a burst of gamma rays, or X-rays, depending on which field you're from. But this photon source can be several MeV, if not GeV in energy. And depending on the intensity regime that you use, these could be monoenergetic photon sources or broadband photon sources. And the duration of the emission is on the order of either the laser pulse or the electron bunch. So we're probably talking 30 or 40 femtoseconds. The other option is just slam the electron beam into a foil and produce Bremsstrahlung, and this would allow us to measure, allow us to generate hard X-ray sources up to GeV. So where next for lasers? Well, my feeling is that the Gemini scale and petawatt and multi-petawatt lasers are going to be really interesting to look at quantum effects. But if we want to do anything useful, this idea of doing 1 shot per day or per hour or even per minute is not really going to cut it anymore. In actual fact, what I'd like to see is to utilize new laser developments such as dipole and try and push this intensity graph down to lower energy, higher pulse repetition rate. And the question is, can we do anything with a few millijoules if we can do this at 1, 10, or a kilohertz? And this means going back to my old thesis data from getting on to 15 years ago now. Initially, we were able to produce electron beams of tens of MeV that were broadband and not very reproducible. They were generally generated in the self-modulated laser wake field regime. And so the quality of the beam wasn't great, but you could do it with less energy and less intensity. And so people generally looked at this and said, well, it's a broadband spectrum, no one's ever going to find that interesting. However, if you're looking for a source of radiography or you're looking to do isotope generation for nuclear physics, then maybe this is going to be useful. And so you can produce maybe a higher charge beam. I've got some undergraduate students running research projects using EPOCH to try and work out whether or not we can increase the charge of these bunches at the expense of the quality of the bunch, but whether or not this allows us to gain in terms of source generation. The second thing, last year I had a student running EPOCH who tried to generate electron beams with about 30 millijoules of energy. The red spectrum here shows what he calculated for just a single pulse, and you see that the electrons never reach high energy. However, if he took that 30 millijoules and he split it into 25 millijoules on 5, and he collided the two beams, he was able to encourage injection at an earlier stage, which allowed the electrons to reach 20 MeV. These are very simplified simulations. They're two-dimensional, and they're probably not quite converged. So the data here is susceptible to critique. But the point I'm trying to make is that if we can start off with a few hundred millijoules and try and get electron beams and then try and perfect that and then start reducing the intensity, if we can demonstrate an electron beam could be generated with tens of millijoules rather than hundreds, then it's not difficult to see that we could produce electron beams at a kilohertz, which now becomes more interesting for people who are interested in total photon number, which include imaging people and also nuclear physicists who are interested in radioisotope production. So where's this going? Well, electron bunch duration will be femtoseconds. If you calculate the peak power from these photon sources, either by Bremsstrahlung or by inverse Compton scattering, you find that you get very quickly up to gigawatts peak power in the multi-MeV photon energy regime. The problem with that is it's very difficult to measure them. I had a conversation with a nuclear physicist who claimed to have a very fast detector to help me with my problem. until he revealed by fast detector he can measure 1 photon every 32 nanoseconds. And I said to him that I have about 10 to the 7 photons in a few femtoseconds. It became clear that this is going to involve some extreme development of diagnostics. I now have a group of nuclear physicists who are helping with this and helping me to design new detectors which would be able to tell something about these new and extreme sources that we can generate. The problem is now I need sort of femtosecond X-ray sources in order to test our ideas. And so this would be an ideal experiment to try on any laser facility is willing to host us, basically. So where do I see this going? Well, I'd like to see some collaborative work, particularly with any group in India who's interested in working with us on some of these things. Clearly, in order to look at the effects of radiation reaction and quantum effects, it'd be nice to see if we could work on reducing the energy spread of electron beams. It'd be interesting to increase the charge, both for the QED studies and also for source development. If we could do this at reduced laser intensity, we could demonstrate the possibility of kilohertz photon sources, which would be nice. The point with that is I wouldn't want to try it with 30 millijoules. I'd like to try it with a few hundred millijoules and slowly reduce the energy. And if we could do that, then we could, in principle, we could prove that a kilohertz system would be able to produce Wakefield accelerated electron beams at kilohertz. Optimizing the spectrum for all sorts of applications, I think, would be interesting. I think this idea of pushing to 1 GeV or 10 GeV or 100 GeV is very important, but it's not the only way to get important results out of a Wakefield accelerator. I think we should also be looking at why we want a GeV. And actually, if we want to produce some interesting isotopes, we probably want somewhere between 10 and 30 MeV instead. And can we do anything to optimize the charge there? In fact, the reason I'm not with you is I'm currently at an experiment on Gemini's target area 2, where we're shooting at 5 hertz and we're trying to optimize the electron beam, not necessarily for the highest possible energy, but also for the highest charge in energy regions of interest. In any case, there are other things we could do. We can measure the size of Compton sources, the size of Bremsstrahlung sources, and actually to do this and to do this developmental work where we study properly and systematically some of the facilities. We don't want to use Gemini. We want to use a facility that can run at least a shot every few seconds rather than a shot every 20 seconds. I think that's pretty much all the slides I have, and I think I've maybe helped catch up a little bit. But as I say, there's lots of people who helped with this work who should be thanked, and I thank them here. I thank you for your attention, and I'm open to any questions you may have. Thank you very much.
Thank you. So, questions?
Can you elaborate on, these kilohertz MeV nuclear reactions that you're talking about?
So, yeah, sure. I'm not talking about kilohertz nuclear reactions. I'm talking about kilohertz sources for nuclear physics, which is a little different. And by that, I mean, for example, so I've done a few nuclear experiments. I did one over at the Isolde facility at CERN. And there we were studying cross-sections of short-lived isotopes. And by short-lived, I still mean minutes or even hours. And the problem that we have, the reason nuclear physics are interested in these isotopes is that although they don't play a major role in reaction chains on Earth, when you've got extreme conditions like supernova explosions, things like titanium-44 is an important waiting point for the nuclear reactions in a supernova explosion. And so they struggle because they want to study these isotopes at an accelerator facility, but the only source that they have is from Geneva. It was actually, there was one in the Paul Scherrer Institute, which was several, I think a few hundred miles away. and they had to go and analyze and take the material and extract titanium-44 and then take it over to CERN and put it at the beginning of an accelerator. Now, if we want to produce isotopes that have half-lives of a few minutes or even a few hours, then the number that we want to optimize is not the number of photons per laser shot. It's the number of photons per interesting isotope half-life. And so if that interesting isotope half-life is on the order of a few minutes, we want to get as many photons or ions or electrons, depending on what we're trying to generate, into this source as quickly as possible. And so maybe using a kilohertz system and taking a small hit in either maximum electron energy or number of electrons will actually enhance the number of isotopes that we can generate. And as I say, we're going to do this kind of experiment, you'd have to extract the isotope at the end anyway. So the whole noise issue that we often have with laser plasma interactions actually disappears. We just bombard a sample with as many electrons as we can for, I don't know, an hour. And then we take that sample, we extract the isotope, and we put it at the beginning of the accelerator and study the nuclear physics of a relatively short-lived isotope.
Another question here.
Yeah, that result on optical injection using 30 millijoule kind of laser. So was this experiment was in the linear regime or non-linear regime? I mean, was the intensity was sufficient to enter into the non-linear regime, or injection was done in the linear regime itself?
It would be probably still just in the linear regime. It's slightly non-linear, but the second laser was counter-propagating in order to encourage injection. So, I mean, it got up to about, but as I say, this is a simulation. These are simulation results. So I think you can probably only take these with a certain amount of confidence.
What kind of density and plasma length was considered here?
This is density of a few 10 to the 18. Basically, it was pretty much matched for a 40 femtosecond pulse in the sort of classical laser wave field acceleration regime. So I think that's about a few 10 to the 18, maybe up to 10 to the 19 electrons per cubic centimeter. And the A naught of the laser, well, it was focused to about 7 microns, I guess, in about 40 femtoseconds. So it's about a terawatt system. What would that be? That'd be about 10 to the 18 watts per square centimeter. So it's probably just in the linear regime.
Okay, thank you.
Welcome.
Okay, so I think that was all from our side. So thanks very much.
Thank you very much.